How to predict laminar to turbulent fluid flow transition. Imagine watching a stream of water flow smoothly over a pebble, then suddenly becoming chaotic and frothy. That change from calm to turbulent flow is what we want to predict. Understanding when this shift happens is key in fluid mechanics and many engineering applications. It all starts with the Reynolds number, a number that compares the forces pushing the fluid forward to the forces resisting it. When the Reynolds number is low, the flow stays smooth and orderly, called laminar flow. As it increases past a certain point, usually around 2300 in pipe flow, the flow can turn turbulent. But this number isn't the only factor. The shape of the surface, the pressure changes, and the turbulence in the incoming flow all influence the transition. To predict when this change will happen, engineers look at how the boundary layer behaves. Near a solid surface, the fluid sticks due to the no-slip condition, creating a thin layer called the boundary layer. If this layer stays smooth, the flow remains laminar. But if small disturbances in this layer grow, they can cause the flow to become unstable and turn turbulent. Scientists use mathematical tools like the Orr-Sommerfeld equation to analyze these disturbances. This equation helps determine if small waves or ripples in the flow will grow or fade. When they grow, the flow is on its way to becoming turbulent. Empirical models also help predict transition points. These models are based on experimental data and stability theory. For example, the Michel criterion looks at local boundary layer conditions to estimate where transition might start. The e to the power of n method tracks how disturbances amplify as they move downstream. These methods give approximate locations where the flow might change from laminar to turbulent. Computational methods are also used. Direct numerical simulation, which solves all the flow scales directly, is very accurate but takes a lot of computer power. Large Eddy simulation captures large turbulent structures and models smaller ones. Reynolds-Averaged Navier-Stokes models use turbulence models to approximate flow behavior. Some advanced models incorporate transition predictions to improve accuracy. Several environmental factors can speed up or delay the transition. Rough surfaces cause earlier turbulence. Adverse pressure gradients, where pressure increases along the flow, can destabilize the boundary layer. High levels of free-stream turbulence or turbulence in the incoming flow can cause the flow to bypass the usual transition process. Flow separation, where the fluid detaches from the surface, can also trigger turbulence. In practice, engineers combine these methods. They use computational fluid dynamics tools with transition models to simulate flow over aircraft wings, turbine blades, or pipes. This helps optimize designs for less drag, better heat transfer, or quieter operation. To sum up, predicting when laminar flow turns into turbulent flow involves analyzing flow stability through theoretical, empirical, and computational approaches. It depends on parameters like the Reynolds number, boundary layer behavior, and environmental influences. Knowing this helps engineers design more efficient systems and improve performance in many fluid-related applications.